Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The story of Pluto, once hailed as the ninth planet of our solar system, is a tale that intertwines discovery, human curiosity, and the evolving understanding of what it truly means to be a planet. Pluto has always captured the imagination of both scientists and the general public alike. From the moment it was discovered, it seemed like the final missing piece in the cosmic puzzle of our solar system, a distant world quietly orbiting the sun in the frigid outskirts of space. Its status, however, has undergone dramatic changes over the past century, sparking debates that reach beyond scientific circles into popular culture, stirring emotions, nostalgia, and even controversy. The question of why Pluto is no longer classified as a planet is not just a matter of semantics. It is a reflection of how science evolves, how definitions adapt, and how our understanding of the universe deepens over time. Pluto was discovered in 1930 by Clyde Tombaugh, an astronomer at the Lowell Observatory in Arizona. Tombaugh was engaged in a systematic search for a potential ninth planet, often referred to as Planet X, which astronomers hypothesized existed beyond Neptune. Observations had hinted at gravitational irregularities in the orbits of Uranus and Neptune, suggesting the presence of another massive body tugging invisibly at these distant giants. Tombaugh's meticulous comparison of photographic plates eventually revealed a faint, moving point of light, which was recognized as a new celestial body. This discovery brought immediate excitement to the world, and Pluto was hailed as the ninth planet, joining the ranks of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune in the classic planetary lineup. For decades, Pluto occupied a firm place in school textbooks, encyclopedias, and the public imagination. Its small size and distant orbit were noted, but they did not diminish its planetary status. Pluto was unique, smaller than Earth's moon, but undeniably a world with a complex orbit and fascinating characteristics. Its orbit was highly elliptical, taking it closer to and farther from the sun than Neptune in cyclical patterns lasting decades. Pluto also displayed a variety of surface features and a tenuous atmosphere, hinting at geological and climatic complexity. Yet despite these intriguing traits, Pluto's discovery was just the beginning of a journey that would challenge the very definition of a planet. As astronomers observed more of the outer reaches of the solar system throughout the 20th century, it became increasingly clear that Pluto was not alone in its distant neighborhood. Starting in the 1990s, advances in telescope technology and observational techniques led to the discovery of many other small, icy bodies beyond Neptune, collectively known as trans-Neptunian objects. Some of these objects, like Eris, Sedna, and Haumea, were found to be comparable in size to Pluto. The discovery of Eris in 2005, which is slightly more massive than Pluto, posed a particular challenge. If Pluto retained its planetary status, would Eris also be considered a planet? Should every similar object in the Kuiper Belt, a vast region of icy bodies, be elevated to planetary status as well? These questions prompted astronomers to re-examine what it actually means to be a planet. The need for a precise definition became urgent. Until that point, planet had been a term with historical and observational weight rather than strict scientific criteria. The classical notion of a planet was somewhat vague, a sizable celestial body orbiting the sun. But this definition proved inadequate when confronted with the growing number of newly discovered objects in the outer solar system. If size alone was insufficient, and mere orbit around the sun too general, what characteristics truly distinguished a planet from other celestial bodies? The question was more than theoretical. The answer would determine Pluto's fate and potentially redefine the planetary hierarchy of the solar system. In 2006, the International Astronomical Union, or IAU, convened to settle the matter. After intense debate, they introduced a formal definition of a planet within our solar system. According to the IAU, for a celestial body to be classified as a planet, it must meet three criteria. First, it must orbit the sun. Second, it must be massive enough for its self-gravity to overcome rigid body forces so that it assumes a nearly round shape, a state known as hydrostatic equilibrium. Third, it must have cleared its orbital neighborhood of other debris, meaning it has become gravitationally dominant in its path around the Sun. This third criterion, which distinguishes planets from smaller, less dominant bodies, would prove decisive for Pluto. Pluto clearly met the first two criteria. It orbits the Sun, and its size and gravity make it spherical. However, it fails the third. Pluto shares its orbital zone with many other objects in the Kuiper Belt, a region beyond Neptune filled with icy remnants from the solar system's formation. Unlike the classical planets, which dominate their orbits, Earth, for instance, has no comparable body competing for its space. Pluto is just one of many objects in a densely populated region. Because it has not cleared its neighborhood, Pluto does not qualify as a planet under the IAU definition. Instead, it was reclassified as a dwarf planet, a category that acknowledges its spherical shape and solar orbit, while distinguishing it from the 8 dominant planets. The reclassification was met with mixed reactions. Among astronomers, it reflected an important step towards scientific clarity and consistency. The definition allowed for a coherent framework to categorize other distant bodies, avoiding the slippery slope of adding dozens of new planets to the solar system. It also recognized the diversity of celestial objects beyond Neptune, providing a framework to study them systematically. Yet among the public, the demotion of Pluto sparked controversy. For generations, Pluto had been considered a planet, and many felt a sense of loss, as if a cherished piece of childhood knowledge had been erased. News media worldwide covered the debate extensively, and the conversation spilled into popular culture, inspiring books, documentaries, and even cartoons lamenting the change. The emotional attachment to Pluto highlights the intersection of science and society. Discoveries are not made in a vacuum, and the implications of reclassification can resonate deeply with human perception. The story of Pluto's reclassification also reflects the evolving nature of scientific inquiry. Science is not static. It adapts to new evidence, revises outdated notions, and refines its understanding of the universe. Pluto's status demonstrates that even long-held ideas can change when confronted with new data. The case of Pluto also illustrates how definitions in science are not arbitrary, but serve a practical purpose. By defining a planet in terms of orbital dominance, astronomers created a criterion that distinguishes planets from other celestial objects in a way that can be consistently applied across the solar system and potentially to exoplanetary systems as well. The focus on gravitational influence reflects an understanding of dynamic systems and the role that massive bodies play in shaping their cosmic neighborhoods. Moreover, the demotion of Pluto has inspired renewed interest in the outer solar system. Far from diminishing its importance, the reclassification has led to increased exploration and study. Missions such as NASA's New Horizons, which conducted a historic flyby of Pluto in 2015, revealed an unexpectedly complex world, with towering ice mountains, vast plains of frozen nitrogen, and an atmosphere that expands and contracts with its orbit. These discoveries highlight that classification does not equate to significance. Pluto remains a scientifically rich and intriguing object. Its geologic activity, seasonal changes, and interaction with its moons make it a laboratory for understanding planetary processes in extreme environments. The exploration of Pluto has broadened our understanding of how diverse planetary bodies can be, even at the fringes of the solar system. Pluto's journey from planet to dwarf planet also underscores the richness of the Kuiper Belt. Once considered an obscure, empty region of space, the Kuiper Belt has emerged as a key area for studying solar system formation. The discovery of hundreds of icy bodies, some comparable in size to Pluto, provides evidence of the processes that shape the early solar system. Studying these objects helps astronomers understand the distribution of ice, the influence of giant planets, and the chemical composition of primordial material. Pluto, as one of the largest known members of this population, serves as a gateway to exploring this distant frontier, bridging the gap between planets and smaller icy remnants that populate the outer solar system. Public interest in Pluto has not waned despite the reclassification. Cultural representations, advocacy campaigns, and ongoing fascination with its story reflect the enduring human connection to exploration and discovery. Pluto symbolizes the frontier, the unknown, and the thrill of discovery, reminding us that the universe is full of surprises. Its journey from the status of a planet to a dwarf planet is a narrative of curiosity, humility, and the evolving understanding of our place in the cosmos. It demonstrates that science is not just about memorizing facts, but about questioning, observing, and refining ideas in light of new evidence. The debate over Pluto has also influenced the way we teach astronomy. Educators now use Pluto's story to illustrate the scientific method, the importance of definitions, and the dynamic nature of knowledge. It is a case study in how discoveries can challenge existing frameworks and how classification schemes must adapt to encompass new realities. Students learn not only about celestial mechanics, orbital dynamics, and planetary science, but also about the philosophy of science, the sociology of scientific consensus, and the ways in which public perception interacts with technical definitions. Pluto's story thus becomes a tool for critical thinking and scientific literacy, engaging young minds with questions that extend beyond simple memorization. From a broader perspective, the story of Pluto speaks to the vast diversity of objects in our solar system. It reminds us that planets are not the only interesting entities orbiting stars. Dwarf planets, asteroids, comets, and moons all play vital roles in understanding planetary formation, the evolution of the solar system, and the potential for life elsewhere. Pluto, far from being diminished by its demotion, exemplifies the richness of the solar system's outer reaches. Its interactions with its largest moon, Charon, and its complex orbital resonance with Neptune provide insights into gravitational dynamics and celestial mechanics that cannot be gleaned from studying the classical planets alone. The narrative of Pluto is also a testament to human curiosity and the drive to explore. Its discovery, initial classification, reclassification, and subsequent exploration illustrate the iterative nature of science. Each step builds upon prior knowledge, correcting errors, refining definitions, and revealing deeper truths. Pluto's story is not a tale of loss, but one of intellectual growth and expansion of understanding. It encourages us to embrace complexity, to question assumptions, and to remain open to new discoveries that challenge established frameworks. In conclusion, Pluto's reclassification as a dwarf planet is the result of careful observation, rigorous scientific debate, and the need for a coherent definition of what constitutes a planet. While it no longer occupies its former place as the ninth planet of the solar system, its significance has not diminished. Pluto remains a world of fascination, complexity, and scientific value, offering insights into the outer reaches of the solar system and the processes that shape celestial bodies. Its story reflects the evolving nature of science, the importance of precise definitions, and the interplay between discovery and understanding. The question of why Pluto is no longer a planet ultimately tells us as much about humanity's approach to knowledge and exploration as it does about the distant, icy world itself. Pluto continues to inspire wonder, spark curiosity, and challenge our perception of what it means to be a planet, ensuring that it holds a permanent place in the imagination and study of the cosmos. Pluto's discovery opened a window into a realm of the solar system that had long been shrouded in mystery. Its orbit is not just distant, but unusually tilted and elliptical compared to the other planets. Unlike the nearly circular orbits of Mercury through to Neptune, Pluto's orbit swings it closer to the Sun than Neptune for a brief portion of its 248-year journey around the Sun. This eccentric path fascinated astronomers for decades. Early models of the solar system had not predicted such irregular orbits, and Pluto's movement became a case study in the complexities of orbital mechanics. Observing Pluto challenged astronomers to refine their understanding of how celestial bodies interact gravitationally, particularly in the outer regions of the solar system where the Sun's influence is weaker, and where objects are more likely to be perturbed by giant planets or even by passing stars over millions of years. The structure and composition of Pluto provide additional reasons for its enduring intrigue. Its surface is a patchwork of frozen nitrogen, methane, and carbon monoxide with regions that appear to be geologically active. Vast plains of nitrogen ice, such as Sputnik Planitia, exhibit signs of convection and slow movement, hinting at processes that renew the surface over time. This discovery shattered assumptions that small, distant worlds were inert and frozen solid. Instead, Pluto demonstrates that even at the edge of the solar system, complex and dynamic processes can occur. Its thin atmosphere, primarily composed of nitrogen, with traces of methane and carbon monoxide, expands when Pluto approaches the Sun and contracts as it moves farther away. This cyclical atmospheric behavior is unlike anything observed on other planets, emphasizing Pluto's uniqueness and further complicating any simple classification. Pluto's relationship with its moons, particularly Charon, adds another layer of fascination. Charon is unusually large relative to Pluto, with a diameter about half that of its primary. This size ratio results in a gravitationally coupled system where both Pluto and Charon orbit a point in space that lies outside Pluto's surface, effectively making it a binary system. The tidal interactions between Pluto and Charon have locked both bodies into synchronous rotation, so that the same face of each always points toward the other. Beyond Charon, Pluto has smaller moons, Styx, Nix, Kerberos, and Hydra, each with its own quirks. The dynamics of this complex system provide astronomers with insights into orbital evolution, satellite formation, and the long-term stability of multi-body systems. It is a microcosm of celestial mechanics, demonstrating that even dwarf planets can host rich and intricate planetary systems. The reclassification of Pluto also resonates with the history of science as a human endeavor. Science is not static, it is a process of continuous refinement. Definitions evolve as observations improve and new discoveries are made. Pluto's demotion to a dwarf planet exemplifies this principle. Earlier, astronomers had relied on historical and observational tradition to classify planets, but as telescopes became more powerful and surveys of the outer solar system revealed an abundance of similar objects, it became necessary to establish a formal, rigorous definition. This shift demonstrates how science adapts, prioritizing clarity, consistency, and predictive power. It is a reminder that what we consider certain or absolute today may be revised tomorrow as our knowledge deepens and our perspective widens. The broader implications of Pluto's reclassification are profound. It reshapes our view of the solar system as not merely a collection of 9 planets orbiting the Sun, but as a dynamic, diverse region filled with objects of many sizes, compositions, and behaviors. The Kuiper Belt, where Pluto resides, is a treasure trove of icy worlds, each preserving information about the early solar system. Studying these objects allows scientists to trace the migration of the giant planets, the dispersal of planetesimals, and the distribution of volatile compounds critical for understanding planetary formation. In many ways, Pluto acts as a gateway to understanding the outer solar system, bridging the inner planet's terrestrial world with the icy expanses that extend toward the limits of the Sun's influence. Public fascination with Pluto is another significant dimension of its story. Despite its reclassification, Pluto has become a cultural icon. Its story has inspired literature, film, music, and art, often symbolizing exploration, nostalgia, and the human desire to reach beyond familiar boundaries. School children continue to learn about Pluto with a mixture of scientific curiosity and sentimental attachment. Educational programs leverage its narrative to teach scientific principles while also illustrating the evolving nature of knowledge. Teachers use Pluto to engage students in discussions about definitions, classification, and the way scientific consensus develops. This dual role, as both a scientific object of study and a cultural touchstone, ensures that Pluto maintains a unique place in both astronomy and the collective imagination. The exploration of Pluto by NASA's New Horizons mission marked a turning point in our understanding of this distant world. Launched in 2006, the spacecraft traveled over 9 years and 3 billion miles to reach Pluto in July 2015. The flyby provided unprecedented high-resolution images and data, revealing a complex landscape of mountains, plains, valleys, and potential cryovolcanoes. The images of Sputnik Planitia, a vast, heart-shaped nitrogen ice plain, captivated the public and demonstrated active geological processes, including ice flow and seasonal changes. Observations showed variations in surface composition, with methane-rich regions, water ice mountains, and dark patches indicating tholins, complex organic molecules produced by ultraviolet radiation. The mission confirmed that even a small, distant world like Pluto is capable of sustaining a dynamic environment, challenging previous assumptions about the limitations of planetary processes at the edge of the solar system. Pluto's orbit continues to intrigue scientists as well. Its resonance with Neptune, a 3-to-2 orbital ratio, ensures that the two bodies never collide despite crossing paths. This orbital resonance provides a natural laboratory for studying gravitational interactions, orbital stability, and the long-term evolution of planetary systems. Understanding such resonances has implications far beyond Pluto itself, informing theories about the migration of planets in our solar system and even the dynamics of exoplanetary systems around other stars. Pluto, once thought of as a marginal planet, now plays a central role in understanding the architecture and history of planetary systems. The classification debates surrounding Pluto also illustrates the importance of terminology in science. Words like planet, dwarf planet, and small solar system body are not just labels. They shape how we approach research, organize knowledge, and communicate discoveries. By defining dwarf planets, astronomers created a category that accommodates Pluto and similar objects without diluting the concept of a planet. This allows for meaningful comparisons between celestial bodies and ensures that scientific discourse remains precise. At the same time, it acknowledges that these objects, while not planets in the classical sense, are still significant in their own right, deserving study and attention. Pluto's reclassification did not diminish its importance in the eyes of scientists. Rather, it has highlighted its uniqueness. Its diverse surface, tenuous atmosphere, complex orbital interactions, and dynamic moons make it an extraordinary subject of study. Researchers continue to analyze data from New Horizons, seeking to understand everything from surface chemistry to potential internal oceans. Some scientists hypothesize that beneath Pluto's icy crust, a subsurface ocean of liquid water could exist, kept from freezing entirely by radioactive decay and antifreeze-like compounds. If true, this would place Pluto among the intriguing icy worlds of the solar system that may harbor the conditions necessary for chemical processes, and perhaps even prebiotic chemistry. Such possibilities underscore that planetary status does not equate to scientific value. Even a dwarf planet can be rich with secrets and surprises. The emotional response to Pluto's demotion also provides insight into how humans relate to space. For many, Pluto embodies exploration and the thrill of discovery, evoking a sense of wonder that transcends scientific classification. Its demotion became a topic of public discussion, protests, and even social media campaigns advocating for its reinstatement as a planet. This phenomenon demonstrates that science operates within a cultural context. Scientific decisions, while based on evidence and rigorous reasoning, intersect with human perception, emotion, and tradition. Pluto's story is thus a reminder that science is not merely a collection of facts, but a human endeavor that inspires curiosity, debate, and reflection. As our technological capabilities continue to advance, Pluto remains a prime target for future exploration. Concepts for orbiters, landers, and flybys are under discussion, aiming to probe its atmosphere, geology, and potential subsurface ocean in greater detail. Studying Pluto and similar dwarf planets provides a window into the processes that shape not only our solar system, but potentially planetary systems around other stars. By understanding the composition, dynamics, and evolution of these distant worlds, we gain perspective on the variety of planetary systems that may exist throughout the galaxy. In reflecting on Pluto's journey from discovery to reclassification, it becomes clear that the story is as much about human curiosity as it is about the celestial body itself. Pluto challenges our preconceptions, invites us to question definitions, and encourages us to expand our perspective beyond the familiar planets. Its orbit, composition, moons, and dynamic surface are a testament to the diversity of worlds that exist in the cosmos, reminding us that our solar system is a complex and vibrant place, far richer than the classical 9-planet model once suggested. Pluto's reclassification does not diminish its importance. It redefines the way we understand it, framing it as part of a larger story of discovery and exploration. Pluto's narrative also illustrates a broader principle in science, that understanding is always provisional, subject to revision as new evidence emerges. Just as Pluto's status has evolved, so too may other concepts in astronomy and planetary science. The search for exoplanets, the study of asteroids and comets, and the exploration of icy moons like Europa and Enceladus continue to challenge and expand our definitions and categories. In this way, Pluto serves as a symbol of the dynamic and evolving nature of scientific knowledge, highlighting the importance of adaptability, critical thinking, and the willingness to question assumptions. Ultimately, the question of why Pluto is no longer a planet is more than a technical matter of classification. It is a story about discovery, about the refinement of knowledge, and about the human desire to explore and understand the universe. It illustrates the interplay between observation and theory, between evidence and definition, and between scientific reasoning and cultural perception. Pluto's journey from ninth planet to dwarf planet encapsulates the ongoing adventure of science, reminding us that the cosmos is vast, mysterious, and full of surprises waiting to be discovered. Beyond its immediate scientific significance, Pluto serves as a case study in the evolving nature of classification systems in astronomy. The discovery of Eris in 2005, a distant object slightly more massive than Pluto, was a key catalyst in redefining the concept of a planet. Prior to Eris, Pluto had been an outlier, but the realization that many other large icy bodies existed in similar orbits forced astronomers to confront a fundamental question. Should we continue to label every sizable body in the outer solar system as a planet? The answer, eventually codified by the International Astronomical Union, was no. By creating the category of dwarf planets, the IAU preserved the notion of planets as dominant bodies in their orbits, while recognizing the importance of Pluto and similar bodies. This decision illustrates how classification in science is not arbitrary, but a tool to organize knowledge in a coherent and practical way, reflecting both physical reality and our understanding of dynamical processes. Pluto's relationship with other dwarf planets highlights the diversity of worlds in the outer solar system. Eris, Haumea, Makemake, and Ceres, the largest object in the asteroid belt, each offer unique insights. Eris, located in the scattered disk region beyond the Kuiper belt, is similar in size to Pluto, but slightly more massive, reinforcing the idea that Pluto is part of a broader population of icy bodies. Haumea is remarkable for its elongated shape, rapid rotation, and family of smaller moons, revealing unusual formation and collisional histories. Makemake, slightly smaller than Pluto, possesses a thin methane atmosphere and highly reflective surface, providing further evidence of the varied processes shaping these distant worlds. By comparing Pluto to its fellow dwarf planets, astronomers can investigate patterns of composition, geology, and orbital behavior, uncovering clues about the formation and evolution of the solar system's outer regions. The Kuiper belt itself is central to understanding why Pluto cannot be classified as a planet. This vast region, extending from roughly 30 to 50 astronomical units from the Sun, contains thousands of icy bodies, remnants of the primordial disk from which the solar system formed. Unlike the 8 dominant planets, which cleared their orbits of smaller debris, Pluto is embedded within a crowded zone of similar objects. Its inability to dominate this region underscores its classification as a dwarf planet. Yet, this crowded environment is scientifically invaluable. By studying the Kuiper belt, scientists gain insight into the distribution of mass in the early solar system, the migration of giant planets, and the processes that allowed smaller bodies to survive in stable orbits over billions of years. Pluto's status as one of the largest known Kuiper belt objects makes it a critical reference point for understanding these dynamics. Exploring Pluto also illuminates the diversity of planetary geology. Unlike many small bodies in the solar system, Pluto exhibits complex surface features and evidence of past or ongoing geologic activity. The discovery of vast nitrogen ice plains, towering water ice mountains, and dark tholin deposits reveals a world shaped by both internal and external forces. Cryovolcanism, the eruption of volatile ices instead of molten rock, may have contributed to the formation of some regions, while sublimation and deposition of surface ices produce seasonal changes in appearance. Pluto's thin atmosphere, which can freeze onto the surface or expand as it approaches the sun, further demonstrates the interplay of temperature, pressure, and surface composition. These dynamic processes challenge earlier assumptions that small, distant worlds are static, illustrating that even dwarf planets can be geologically active and scientifically rich. Pluto's complex orbital relationship with Neptune is another area of fascination. The 3-to-2 resonance between Pluto and Neptune ensures that, despite overlapping orbits, the two bodies never collide. This stable orbital configuration results from gravitational interactions over billions of years, offering a natural laboratory for studying resonance phenomena. Orbital resonances like this one are common throughout the solar system, influencing the distribution of asteroids, moons, and trans-Neptunian objects. Pluto's behavior demonstrates the delicate balance of gravitational forces, and studying it informs models of orbital evolution, stability, and the long-term architecture of planetary systems. Such studies are essential for understanding not only our solar system, but also exoplanetary systems, where resonance plays a key role in the arrangement of planets around other stars. The New Horizons mission brought Pluto into unprecedented detail, fundamentally transforming our understanding of this distant world. The spacecraft revealed a topography filled with surprises: deep canyons, mountains composed of water ice, smooth plains shaped by glacial flow, and diverse surface compositions indicating past and ongoing geological processes. Observations of Pluto's atmosphere revealed haze layers, dynamic escape of gases into space, and chemical interactions producing complex organic molecules. These discoveries underscore the notion that classification does not define significance. Even as a dwarf planet, Pluto presents extraordinary scientific value. The images and data captured by New Horizons transform public perception as well, sparking renewed interest in outer solar system exploration and highlighting the power of direct observation in reshaping scientific understanding. Culturally, Pluto's story resonates far beyond the scientific community. The debate over its planetary status captured global attention, inspiring books, documentaries, educational programs, and artistic works. For many, Pluto represents more than a celestial object. It embodies exploration, curiosity, and the wonder of the unknown. Its demotion sparked emotional responses, social campaigns, and discussions about the role of science in society. This interplay between scientific classification and public perception demonstrates that science operates within a cultural context, where facts and definitions intersect with human sentiment and imagination. Pluto's narrative serves as a reminder that our understanding of the universe is deeply intertwined with the human experience of wonder, nostalgia, and discovery. Education has embraced Pluto as a tool for teaching not only astronomy, but also critical thinking and scientific methodology. Teachers use Pluto's story to illustrate how definitions evolve, how evidence informs classification, and how scientific consensus develops through debate and review. Students learn that science is not static, and that knowledge is provisional, subject to revision when new data emerges. Pluto becomes a gateway to discussions about planetary science, orbital mechanics, atmospheric physics, and the sociology of science. By engaging with Pluto's history, learners explore both the technical aspects of astronomy and the broader processes by which humanity understands the natural world. The broader implications of Pluto's story extend to planetary science and exoplanetary research. As astronomers discover planets around other stars, questions about classification, orbital dominance, and planetary characteristics arise repeatedly. The criteria developed for dwarf planets and planets in our solar system offer a framework for interpreting distant exoplanetary systems, where observations are limited and indirect. Pluto, through its reclassification, serves as a precedent for how to approach categorization in astronomy, establishing criteria that are both physically meaningful and applicable across diverse environments. In this way, Pluto's story informs not only our understanding of the solar system, but also our approach to studying the broader cosmos. Even as technology advances and missions probe deeper into space, Pluto remains a benchmark for the outer solar system. Its composition, orbit, and dynamic processes provide a reference for understanding other trans-Neptunian objects in distant icy worlds. Studying Pluto helps astronomers model the early solar system, understand planetary formation, and explore the interactions between giant planets and smaller bodies. Its existence challenges preconceptions, inspires new questions, and highlights the complexity and diversity of celestial bodies beyond the classical planets. In many ways, Pluto exemplifies the richness of the solar system's outskirts, demonstrating that fascination and scientific importance are not limited to objects with planetary status. The philosophical and educational lessons of Pluto's journey are equally profound. Its story illustrates that science is a human endeavor, shaped by observation, debate, evidence, and consensus. Classification systems, while designed for clarity, are tools rather than immutable truths. Pluto's demotion highlights the importance of remaining open to new evidence, questioning assumptions, and embracing complexity. It reminds us that curiosity drives exploration, and that understanding is a process rather than a fixed endpoint. Pluto, as a dwarf planet, continues to embody the spirit of discovery, challenging scientists and the public alike to look beyond preconceived notions and engage with the universe in new ways and thoughtful ways. In considering the legacy of Pluto, it is clear that its reclassification does not diminish its significance. From its discovery by Clyde Tombaugh to the revelations of New Horizons, Pluto has remained a source of fascination, discovery, and scientific advancement. Its dynamic surface, complex orbital behavior, and interactions with moons in the Kuiper Belt exemplify the richness of small, distant worlds. The debates surrounding its classification reflect the evolving nature of science, the role of evidence in shaping understanding, and the cultural resonance of celestial objects. Pluto stands as a testament to the complexity of the cosmos, the power of human curiosity, and the ongoing journey to comprehend our solar system and beyond. As humanity looks toward the future, Pluto will continue to inspire exploration and discovery. It serves as a reminder that the universe is vast, diverse, and filled with worlds that defy simple categorization. Its story challenges us to think critically, to embrace new evidence, and to expand our understanding of what constitutes a planet, a system, or a world. Pluto's journey from planet to dwarf planet is not a story of loss, but one of growth, refinement, and the deepening of knowledge. In studying Pluto, we study not only a distant icy world, but also the processes by which humans seek to understand the cosmos, highlighting the enduring connection between exploration, science, and the imagination. Pluto's system of moons further enriches its scientific importance and illustrates the complexity of dwarf planet systems. Charon, the largest of Pluto's moons, dominates the system with a diameter about half that of Pluto itself. This unusually large size ratio creates a unique binary dynamic, with both bodies orbiting a common center of mass that lies in the space between them, rather than within Pluto's body. The synchronous rotation of Pluto and Charon, where each shows the same face to the other, demonstrates tidal locking, a phenomenon that occurs when gravitational forces create a stable rotational configuration over long timescales. Beyond Charon, Pluto hosts 4 smaller moons: Styx, Nix, Kerberos, and Hydra. Each of these moons exhibits unique orbital characteristics, including irregular shapes, rapid rotation, and complex resonances with both Pluto and Charon. Together, this system provides a natural laboratory for studying gravitational interactions, satellite formation, and the evolution of multi-body systems, which are important for understanding not only the outer solar system, but also exoplanetary systems that may host similar dwarf planet-moon configurations. Pluto's seasonal changes and atmospheric phenomena also highlight the richness of dwarf planet science. Its highly elliptical orbit, combined with a long orbital period of 248 Earth years, produces extreme seasonal variations. As Pluto approaches the Sun, surface ices sublimate, forming a tenuous atmosphere primarily composed of nitrogen, with traces of methane and carbon monoxide. This atmosphere expands as Pluto moves closer to the Sun and partially freezes onto the surface as it moves away, a cyclic process that affects surface pressure, temperature, and ice distribution. Observations from Earth-based telescopes and New Horizons reveal that haze layers form in the atmosphere, extending hundreds of kilometers above the surface. These layers scatter sunlight and contribute to photochemical reactions, producing complex organic molecules that darken the surface over time. Such dynamic processes are remarkable for a small, distant world and demonstrate that dwarf planets can be active, changing environments rather than static, frozen bodies. The Kuiper Belt, the region in which Pluto resides, provides further context for understanding why Pluto cannot be classified as a full-fledged planet. Unlike the 8 classical planets, which cleared their orbital zones of smaller debris, Pluto shares its region with numerous other icy bodies of similar size and composition. Some of these objects, like Makemake and Haumea, rival Pluto in size and complexity. The presence of this population illustrates that the outer solar system is a dynamic, crowded environment, with gravitational interactions shaping the orbits and distribution of objects. Studying the Kuiper Belt allows astronomers to reconstruct the early history of the solar system, including the migration of Neptune and other giant planets, the scattering of planetesimals, and the retention of primordial ices. Pluto, as one of the largest and most accessible Kuiper Belt objects, acts as a gateway to understanding these processes and offers a benchmark for comparison with other distant bodies. Culturally, Pluto's demotion sparked widespread discussion, highlighting the human dimension of science. For generations, school children had memorized Pluto as the 9th planet, and its reclassification was met with surprise, disappointment, and even protest. News outlets, social media, and popular culture amplified the debate, making Pluto a symbol of change, curiosity, and debate in science. Educational programs leverage this story to teach critical thinking, illustrating that definitions in science are not fixed, but evolve with new knowledge. Pluto's narrative became an opportunity to discuss the nature of discovery, the importance of evidence, and the way scientific consensus forms. In this sense, Pluto transcends its physical existence, becoming a cultural touchstone that reflects both our fascination with the cosmos and our capacity to adapt understanding in the face of new information. The exploration of Pluto has also reshaped our expectations for the outer solar system. Before New Horizons, scientists imagined Pluto as a small, inactive, icy rock. Instead, the mission revealed a geologically diverse and active world, with nitrogen glaciers, water ice mountains, and potential cryovolcanic features. These discoveries have altered the way astronomers think about dwarf planets and trans-Neptunian objects. No longer are these bodies considered inert leftovers of solar system formation. They are active, evolving worlds with complex histories and dynamic surfaces. This shift challenges long-standing assumptions and emphasizes the importance of direct observation and exploration in refining our understanding of planetary processes. In the broader context of astronomy, Pluto's story informs our understanding of planetary formation and classification beyond our solar system. As thousands of exoplanets are discovered orbiting distant stars, questions about what constitutes a planet, a dwarf planet, or a minor body arise repeatedly. The criteria established by the IAU for distinguishing planets and dwarf planets provide a framework for interpreting these discoveries, helping astronomers categorize distant worlds in a meaningful way. Pluto's reclassification thus serves as a precedent for studying exoplanetary systems, highlighting the importance of gravitational dominance, orbital dynamics, and size in defining planetary status. By applying these principles to other star systems, scientists can better understand the diversity, evolution, and architecture of planetary systems throughout the galaxy. Pluto's story also highlights the value of curiosity-driven exploration. Its discovery, long before the era of modern telescopes and space probes, was a product of meticulous observation and a desire to uncover the unknown. The subsequent reclassification and New Horizons mission reflect humanity's commitment to questioning assumptions, pursuing knowledge, and exploring the farthest reaches of our solar system. Pluto embodies the spirit of discovery, reminding us that scientific progress often involves reevaluating what we think we know and embracing complexity rather than simplicity. Its journey from 9th planet to dwarf planet illustrates the iterative nature of science, where new evidence refines understanding and reshapes conceptual frameworks. Even now, Pluto remains a source of fascination and inspiration. Its interaction with Charon, the presence of smaller moons, and its dynamic surface processes provide fertile ground for ongoing research. Studies of its geology, atmosphere, and potential subsurface oceans continue to yield insights into the conditions and processes present on distant icy worlds. In addition, comparative studies with other dwarf planets and trans-Neptunian objects offer a window into the diversity of the solar system's outer reaches. These investigations enhance our knowledge of planetary formation, migration, and evolution, contributing to a deeper understanding of how the solar system, and potentially other systems, came to be. Pluto's enduring significance is a testament to the fact that scientific classification does not dictate value. While it may no longer be considered a planet, Pluto remains an extraordinary world with unique features and mysteries waiting to be explored. Its story challenges us to think critically about definitions, to appreciate the richness of small and distant worlds, and to recognize that scientific understanding evolves as our observational capabilities and theoretical frameworks improve. Pluto exemplifies the interplay between exploration, observation, and conceptualization, demonstrating that science is a dynamic process rather than a collection of static facts. In reflecting on why Pluto is no longer classified as a planet, it becomes clear that the answer lies not in diminishment, but in refinement. Pluto meets many of the criteria for planetary status, including orbiting the Sun and being spherical in shape, but it does not dominate its orbital region. By defining planets in terms of gravitational dominance, astronomers created a consistent, logical framework that can be applied across the solar system and beyond. This framework allows for the classification of a wide range of celestial bodies while preserving the concept of planets as major, dynamically influential worlds. Pluto, reclassified as a dwarf planet, continues to provide invaluable insights into the solar system's formation, evolution, and diversity. Ultimately, Pluto's journey from discovery to reclassification is a story of scientific growth, human curiosity, and the evolving understanding of the cosmos. It demonstrates that knowledge is provisional, that definitions evolve with new evidence, and that exploration leads to deeper insights about the universe. Pluto continues to inspire wonder, curiosity, and scientific inquiry, reminding us that the solar system is far more complex and diverse than early models suggested. Its status as a dwarf planet does not diminish its importance. Instead, it underscores the richness of the solar system and the ongoing quest to comprehend the distant and mysterious worlds that lie at its edge. Pluto remains a beacon of exploration, a symbol of the unknown, and a testament to the enduring human desire to understand the cosmos. From the meticulous observations of Clyde Tombaugh to the groundbreaking data from New Horizons, Pluto has challenged assumptions, revealed unexpected complexity, and reshaped the way we think about planets and dwarf planets alike. Its story continues to unfold as scientists study its surface, atmosphere, and moons, uncovering new mysteries and refining our understanding of the outer solar system. In every sense, Pluto embodies the spirit of discovery, demonstrating that even the smallest, most distant worlds can offer profound insights into the nature of the universe. In the end, the question of why Pluto is no longer a planet is not a story of loss, but of discovery, understanding, and scientific progress. It is a narrative that highlights the evolving nature of knowledge, the interplay between observation and classification, and the importance of curiosity in driving exploration. Pluto, as a dwarf planet, continues to captivate scientists and the public alike, offering a window into the dynamics, diversity, and beauty of the solar system's outer reaches. Its legacy is not defined by a label, but by the wealth of knowledge, inspiration, and wonder it continues to provide. Pluto's story reminds us that science is an ongoing journey, not a destination. The demotion of Pluto is not a mark of failure, but a reflection of the growth of human understanding, a step forward in the quest to categorize, comprehend, and explore the cosmos. As technology improves, new missions are launched, and our gaze extends further into the solar system and beyond. Pluto will remain a guiding light, a world that challenges, inspires, and enriches our understanding of the universe. Its legacy as a dwarf planet is secure, not diminished, and its significance continues to grow with every new discovery and observation, cementing its place in the narrative of space exploration and human curiosity.